All right. We are in Tuesday, week 7. Can you believe we're in week 7? What the heck? Next week is the last week. We're in the home stretch. We're on the last chapter. Chapter 10. Chapter 10 is our final chapter. And chapter 10 has to be my favorite. And I think I said this about everything. Every chapter I say that, don't I? Oh well, I love it all. Math. So I am back full time at the high school. We started yesterday, so I might not be quite as quick as answering messages, but I'll do the best I can, especially since tomorrow we have an all-day training at that starts at 7:30 a.m. and doesn't get done till 3:30. So I probably won't be able to check in at all between 7:30 and 3:30 tomorrow. But I will, once I get off work and get home, I will make sure to jump in and check. And it's exhausting. We're this week we don't have students yet. So we are doing our planning, we're setting up our classrooms, we're getting our trainings, and it's a lot. But I am here, I am excited. Next week we have our final projects due, and we have our last test. The test covers chapters 8, 9, and 10. So I don't believe that 8 is like explicit, because 8 is like topics that support 9 and 10. So the bulk of the test is going to be 9 and 10. There's a little bit of 8 there, but it is like the bulk of it is 9 and 10, because 8 is like a supporting character. It gave us all the foundation. So today we're actually not going to be doing any math. We'll do all of the math on Thursday. Um, no, I I would expect, so the question for those of you who can't read the comments says, do you expect each graph and table in the written report to have their own analysis and conclusion? Now, if you created a table and you used that table to create a graph from it, then I'm not expecting separate, or you could reference, like during when you're writing stuff down, you could say, I could see based on the graphs, this graph shows me this graph shows me that. You can lump them together. But I don't want you putting graphs there that don't help at all, or that are meaningless, or just there because they're pretty. I want them to be meaningful. So, you're at least going to want to show kind of what you got from it. It doesn't necessarily need to have a big, huge explanation. You can even just you can see by the blue and red bar graph that men tend to sleep more hours than women. I just made something up. You can just like real quick like that without doing any extra math, and just kind of use that as a jumping off point for something else. So it doesn't have to be deep. Is that hopefully that helped and didn't cause you grief. I'm going to once again say, because many people will be watching this that maybe didn't see it before, the written report, not including graphs and tables and raw data, I expect the written report to be page and a half, 2 pages. It could be longer than that, but I have not encountered a good written report that was less than a full, like, page and a half. Um, Maybe somebody got like a low C on one that was only 1 page, but you're not going to get everything across with just one full page, especially since that page is going to have your written work on it, because you have to have one hand calculated thing. You can't, no, I'm just saying that if you took all the graphs and tables out of it, your writing and all of that would be 1 page, or like a page and a half, 2 pages minimum. Okay. So you have a choice. You could have all of your graphs and tables and your raw data on a spreadsheet. It doesn't have, okay, I'll jump back on that. And then you could reference them in your paper. So you don't put the graphs and tables in your paper, and you say, on the Excel sheet, this graph shows this. So you're referencing the Excel spreadsheet that you're including. The that Excel spreadsheet doesn't need to be super organized. If I can find it on there, it can be kind of like rough work where I just have graphs in different places. It doesn't have to be super organized. As long as if you say, referencing the blue and red bar graph. And then if I pop into your Excel, I want to be able to find one blue and red bar graph if you choose to do it that way. If you don't include the raw data and the graphs and the tables directly in your paper, you'll need to give me the spreadsheet. If everything from your spreadsheet is included in your Word document or whatever type of document you're using, if you've put all of it in there as part of your organization, you don't have to give me the Excel spreadsheet. Does that make sense? So it's really up to you and your own stylistic choices. Okay, so yeah, if and I don't care if even if there's extra stuff on the Excel that didn't land in your paper, is it's okay. I'm going to whatever you reference in your paper, that's what I'm going to look at in the Excel. Yes, go ahead.
I have it's very complicated somehow what I'm doing.
Okay.
And so, I just have things everywhere and I kind of want you to see what I've been doing because it seems pretty complicated, but
Right.
then it's almost like too much. So that's what I mean by I delete it and I'm not sure if you want to see it or really you
I
just want the end result.
I don't need to see the process. If you have extra graphs that you didn't use and don't want to use, it's okay if you delete them. I'm just saying it's okay if you don't.
Okay, I understand.
Yeah. This is, it's kind of like showing your work on a test. You might have done some math that didn't lead you anywhere, and then you just decided not to use that math. And so you did more. The Excel spreadsheet would be your work. But some people take that work and put it in the middle of their paper because they like to be able to read and say, the next graph will show you yada, 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 yada. And, have it be that flow. Either way is fine, whatever your style is. I've been teaching this class long enough now that I'm comfortable with either seeing everything on your Word document or referencing the Excel sheet. The only thing you can't reference is the data that you submitted for that assignment because that was like the rough draft of a paper in your English class. You don't turn in the rough draft, or you don't say in the main paper, you don't say per my rough draft. You don't do that in your English class, right? You're not going to say per my rough draft. Go back and look at that. No, that was like just that is like I'm making sure that you are processing through it all, making sure you're working on things. And I grade them fairly leniently. I don't grade it as if I'm a writing 121 teacher. As long as I understand what's happening, if your spelling is not perfect, your grammar isn't perfect, as long as I understand what's happening, as long as it's not incoherent, I'm cool with it. I'm not looking for writing 121 quality work. I'm not looking for that. I'm just looking to be able to read through it and understand, here's your question. Here's all of the things that my work showed me that helped me answer the question. Here's one little math problem that I did by hand. Look how cool that is. And then, and this is what it shows me. And here I go. Don't forget your one hand calculated formula. It's a requirement that I have to put in there. You can use an equation editor to edit it, put it in there if you want to. You can type it in using very like the symbols on your keyboard, which make it look kind of ugly, but that's fine. Or some people will hand write it on a piece of paper, take a picture of it, crop it, and put it in the middle. That's fine too. As long as you are showing me your work, the one hand calculated problem. Now, if you're doing, let's say you calculated mean, and that is your hand calculated problem, show me that you added these things together and divided by this other thing, but put it in your calculator. Don't use your brain to add up 50 things and same thing, if you're calculating a z-score, type out the formula that you filled in, put it in your calculator, and then give me the equals. I'm not asking you not to use your calculator. I'm just asking you to show me I can fill in all of these numbers into this formula and get this answer. Does that make sense? Okay. So let's talk about what we're going to do today. So we are in chapter 10, we do 10.1, 10.2, and 10.3. What we're doing is we're kind of taking our confidence intervals, which hopefully you're comfortable enough with confidence intervals that I can take that concept and bring it even a little bit more rich and add a little bit more to it. Hypothesis testing is what we're going to be doing, and it is actually pretty cool. I'm hoping you find it as cool as I do. Probably not as cool as I do, but just a little bit cool. Okay, so the first thing we're going to talk about is we're going to pretty much talk about what hypothesis testing is, and we're going to talk about the setup. And then we're going to talk about the different types of errors that you can have and how to write a conclusion without doing the middle portion. We're basically writing our thesis statement and writing our conclusion without doing the middle stuff yet. And then, and we're going to start with 10.2, and we're going to talk about kind of different ways to look at our hypothesis testing, different ways to test it without doing the math. Then Thursday, we're going to do hypothesis testing with proportions and then hypothesis testing with means. And the math is not a ton different than what we did in chapter 9. So it will reinforce what we did in chapter 9 and just build on it a little bit. So it won't be, it's using the same like new standard deviation for both mean and proportion, using the z-scores and the t-values. So it's all very similar to what we did in chapter 9. So it'll reinforce it and it'll add to it. So that's what's going on. We have no math today. You don't even need your calculator. You can set it off to the side and just leave it be. And it's just a lot of, we're just gonna just roll with it. Okay. So what a hypothesis is, I'm sure you've taken science classes. If not in college, then definitely in high school. A hypothesis, it's a statement that we make that we think something is. So we will make a statement that we think might be true about a characteristic of a population. So um, I could say that I think that cats actually sleep more than 18 hours a day. That might be my hypothesis, something that I wanted to show is true. I'm just saying that as I glanced over and saw my kitty sleeping. Or I could say that I think that teenagers check the notifications on their phone more than 100 times per day. So I'm just making a statement. That's my hypothesis. Now, I'm going to teach you Thursday, I'm going to teach you all of the math that you can need in order to show the hypothesis is true or show that it probably isn't true. But today we're just going to talk about how to set that up, how to write a hypothesis. Okay, here's some examples of hypotheses that we might see, that we might test. In 2008, 62% of American adults regularly volunteered their time for charity work. A researcher believes that this percentage is different today. So there was a study in 2008 that about volunteer time, and there's a researcher, for some reason, I don't know, maybe his own life observations, whatever, he thinks that that's different. He thinks that it's no longer 62%. He doesn't say greater than, he doesn't say less than, he just says it's different. Here's another one. According to a study published in March 2006, the mean length of a phone call on a cell phone was 3.25 minutes. A researcher believes that the mean length of a call has increased since then. So he looks at a previous study, but that study was 19 years ago. So based on his own life experience, maybe, I don't know, he thinks people talk longer on the phone today than they used to. Using an old manufacturing process, the standard deviation of the amount of wine put in a bottle was 0.23 ounces. With new equipment, the quality control manager believes the standard deviation has decreased. So whatever this new equipment is, he thinks it's made it more consistent. And that's what he's testing. He's going to test if it's more consistent. So a lot of companies actually do stuff like this type of testing when they are doing new and improved is kind of their way to show, hey, this is new and improved. It is more consistent. So these are the claims that we're going to look at as we're setting up our hypothesis testing. All right. So now with these statements, we can only use sample data. Because if we have the population data, we don't have to make a hypothesis. We already know the information about the population. So why would I hypothesize if I already know, if I already have all that info? So there you go. It's sample data. So we use hypothesis testing. We make a statement, and then we use sample evidence and then with probability to determine whether or not it would be unusual to get a result that we got with our sample evidence. So we've been using the rule of thumb that something's unusual if it occurs less than 5% of the time. But depending on the importance or severity or whatever of the thing that we're looking at, we're going to change that 5% depending on what we're looking at. As I've said before, if it's a space shuttle, then you're going to have stricter requirements than if you're putting a garden in your backyard. So depending on what we're looking at, we're going to have use different values than 5%. And I'll give you the value every time. You don't have to come up with them on your own. All right. So here's our steps. So the first thing we do is we're going to make a statement regarding the nature of the population. We're going to say that I believe cats sleep more than 18 hours a day. So you make a statement. Before you have collected any data, you will make your statement. After you make your statement, then you collect the evidence that you need, the sample data, to test that statement. So um, whatever size sample that you want to use, you collect that sample, and then we move on to testing it. Analyze the data, the math that I teach you on Thursday, we will do that to determine whether the statement that I made is plausible based on my evidence. So basically what we're doing, we're going to construct a confidence interval. So I have my confidence interval, and we're going to determine does what I got, the evidence that I have, does it land within my confidence interval or does it land out here? That's what we're doing. So we're just comparing our data to the confidence interval that we created. Not too bad, right? Yeah, you don't know. You'll know on Thursday. Okay. So anytime anything has this little subscript 0, it's called not or null. So the null hypothesis is our statement to be tested. It's the original statement. The null hypothesis is like the past studies that we have. So if I had a study before that stated that cats sleep 18 hours a day, my null hypothesis is that cats sleep 18 hours a day. That and we believe it is true until we can show otherwise. So whatever our previous studies show, that's our null hypothesis. And it's just H sub 0. Anytime you see anything sub 0, it means that that's like an initial value, or that's like our starting value or starting belief or whatever. Alternative hypothesis, you will see this two different ways. You'll see it as, you'll see it as H sub A, and you will see it as H sub 1. They mean the same thing. So you'll see it both ways, H sub 1 or H sub A. They both are the alternative hypothesis. The alternative hypothesis is what we're trying to show. So if I believe that cats sleep greater than 19 hours or 18 hours a day, my alternative hypothesis is cats sleep greater than 18 hours. So my alternative hypothesis is what I'm trying to prove, what I'm trying to find evidence to support. I'm trying to find evidence to show that my statement is true. So that's what the alternative hypothesis is. You'll see it both H sub A and H sub 1. I think my open math uses H sub A. I can't remember though. And every single term, I look it up after I teach this class to see which one it is because I can never remember. And then I don't remember for the next term. And I'll always think, oh, I'll remember. I don't remember. Okay. So we have 3 different ways that we set up our null hypothesis or set up our hypothesis test. If a two-tailed test, we will see the word different. If it is a two-tailed test, we will see the word different. our null hypothesis is always equal. Notice how on all of these, my null hypothesis says equal, every single one of them. My alternative hypothesis will say not equal to. My alternative hypothesis with a two-tailed test will say not equal to. What this looks like on a curve, my confidence interval looks like this, and I'm looking for, does my actual data land me out there and either above my confidence interval or below my confidence interval? That's why it's a two-tailed test, because we're checking, does it land in either one of those tails? If my sample lands me in either one of those tails, then my alternative hypothesis is likely true, which means my null hypothesis probably isn't. The left-tailed test, if you see less than or smaller than or anything like that, decreased, any of those words, and this is what it's going to look like. We only have this tail. So it is not a complete confidence interval. It's only the lower. So it's only the lower part. So we're looking, does my alternative hypothesis, my sample, land me below that confidence interval? Does it land me down there in the bottom? That would be a left-tailed test. My alternative hypothesis would say less than. Right-tailed test. This is greater than, more, increased, any of these kind of words. So again, I'll draw my pretty picture. We're only using the upper side of our confidence interval, and we're looking, does my sample land me up above? Does it land me in that right tail? And it's going to be greater than. So right-tailed test is greater than. I love that the left-tailed and right-tailed match with a number line. It would totally mess me up if it was like left skewed and right skewed. That seem not right. I'm glad that these are true the way they're supposed to be. So if it's right on the number line, it's greater than. If it's to the left on the number line, it's less than. I'm really glad that these are consistent with that. So any questions so far before I move on? And we're going to be setting some of these up with the examples I gave earlier. So I'm hoping that'll help. Okay. So null hypothesis is our status quo, no difference. It is always true until we have evidence to show it isn't. The null hypothesis is true unless we have evidence to the contrary. We are looking for evidence to support the alternative hypothesis. I'm going to poll a whole bunch of people, have them put, I don't know, Apple Watches on all of their cats. And we're going to look at their sleep data and we're going to determine how much they sleep per day. So that's how we're going to test that, because we're going to have many feline Apple Watches. So that's what it's going to be. Okay, so let's set up our alternative or set up. Does it want me to set them up? Yeah. Let's set these up and let's determine if they're right-tailed, left-tailed, or two-tailed. So we're going to look at each of these examples and we're going to set these up. So in 2008, 62% of American adults regularly volunteered their time for charity work. A researcher believes this percent is different today. So this is my key word. He didn't say greater than or less than. If my evidence, my sample shows that it's significantly less than or shows that it's significantly greater than 62%, then my alternative hypothesis would be supported, correct? So null hypothesis, oh, this is, sorry, two-tailed test. Two-tailed. So my alternative hypothesis, it's going to look like this. We're looking at a proportion. It's 62%, so it is a proportion. So I have P equals 0.62. Because this is a proportion, we use this symbol for proportion. So my alternative hypothesis is that the proportion of people who regularly volunteer is 62%. My alternative hypothesis, I'm going to do sub 1 because that's what they like on this, is that it's different. Whenever we see different, we use not equal to. So this is what our setup looks like. It's a two-tailed test because it could be greater than or it could be less than, and it is different, so it's not equal. All right, let's do the next one. Oh, they have it here too. I do this on purpose. I want to make sure that people who don't watch this and just look at the PowerPoints have it. All right. According to a study published in March 2006, the mean length of a phone call on a cell phone was 3.25 minutes. A researcher believes it has increased. That's greater than, therefore this is right-tailed. It's a right-tailed test. My null hypothesis, always going to be equal. Always going to be equal, and it's mean. So mean length of a phone call. So I'm going to use mu equals 3.25. Though we're using a sample, we are referencing a population. We're making a prediction about the population. That's why we use mu, because we're predicting the population. Null hypothesis always uses equal. Alternative hypothesis. It's greater than, so I say mu greater than 3.25. Important. These numbers will always be the same. These numbers here, they will always be the same. The only thing different about the null and the alternative hypothesis is the sign right here and the subscript. Those are the only things different. The sign and the subscript. The symbol, not really a sign, it's a symbol. Those are the only things different about an alternative and a null hypothesis. Okay, let's do the next one. Yeah. I just said all this stuff. Okay. Using an old manufacturing process, the standard deviation of the amount of wine put in a bottle was 0.23 ounces. New equipment, the quality control manager believes the standard deviation has decreased. Decreased means less than, so this is a left-tailed test. We won't be doing hypothesis testing with standard deviation. I think that that's a section or two later or another chapter. We only do mean and proportion. We stick with those two things because that's what we've already built on. We already built on those two things in chapters 8 and 9. So we won't be doing hypothesis testing with standard deviation, though it's kind of cool when you do it, but we're not going to do it. Okay, so my null hypothesis is sigma because we're talking about a population equals 0.23. My alternative hypothesis is that sigma is less than 0.23. So that's the setup. Any questions on these? Okay, good. Cool beans. All right. So okay, I'm going to tell you these type 1 and type 2 errors that we're jumping into can be kind of confusing. And I am pretty gentle when grading these. So do the best you can. Make sure you answer them even if you're not sure. I can tell you there will be a type 1 and type 2 error on the test, but just make sure you follow the directions completely. And I'm pretty lenient with it. So I'm pretty gentle with grading because I forget which they are. So if I can't remember them, I don't expect you to memorize them, but you have them right in your notes. So um, these are the four different outcomes. You reject the null hypothesis if the alternative hypothesis is true. So if we have evidence to support our alternative hypothesis, then we say we reject the null hypothesis. We say that null hypothesis is not true because I have evidence to say it's not true. This is a correct decision. This is right. We don't reject or fail to reject. I prefer the words fail to reject. You can say it either way. You can either say, I do not reject, or I fail to reject. I don't care which way you say it. I like the words fail to reject. If we fail to reject the null hypothesis, if the null hypothesis is true. So if my evidence doesn't support the alternative hypothesis, then we don't reject the null hypothesis. Then we're like, quite probably the null hypothesis is true. Based on my sample, I can't prove it wrong. So therefore, I don't reject the null hypothesis. So I don't have enough evidence to say the null hypothesis isn't true. Okay, this is where we're going to do the incorrects. So if we reject the null hypothesis, but the null hypothesis is true, this is called a type 1 error, and that is not a correct thing to do. So if my evidence doesn't support the alternative hypothesis, but then I reject the null hypothesis, that's called a type 1 error. So I reject it when I shouldn't. I'm going to just write that. Reject when you shouldn't. Now, a type 2 error in this case, if I don't reject the null hypothesis, but I have evidence to support the alternative hypothesis, that's not a correct thing to do, and that's a type 2 error. So I have, I got a whole bunch of samples back, and based on my evidence, most cats, or a large enough number of cats, that the probability that we would get that many cats in the sample sleeping longer than 18 hours is really, really small. And then I don't reject the null hypothesis, even though my evidence shows that cats sleep longer than 18 hours. That's a type 2 error. So I say fail to reject when we should reject. That is a type 2 error. So rejecting when you shouldn't is type 1. Failing to reject when you should is type 2. As long as you have your notes in front of you, you should be fine. So the two of you that are in this class right now and those who actually watch the video, I'm going to give you a little hint about something on the test. The type 1 and the type 2 error problems on the test, it mentions to answer the question in the context of the problem. There will be a situation you are given, and you need to make sure that you reference that situation. Like maybe it is whether or not cats sleep more than 18 hours, which it's not going to be, but that's the example I keep using. So if I found out that most cats, cats sleep greater than 18 hours a day, and I say we fail to reject the null hypothesis, then that's a type 2 error. So you would say we failed to reject the null hypothesis when our evidence shows that a large number of cats greater than or like the probability of getting a sample that we have is less than 5%. And we should have rejected them. I'm not wording this correctly, but if you just state that, make sure you talk about the actual problem. You mention the cats. Make sure you mention the cats when you're talking about the type 2 error. I'm going to give you some examples of wordings here in a minute, but make sure that it says in context of the story or the situation, that you are mentioning whatever the story is about. You don't just give me the definition of a type 2 error. You actually mention the story. All right. So let's actually look at what a type 1 and a type 2 error would be. They use a heck of a lot of words for this, but this will give you an idea. So we're looking at the 62% of Americans regularly volunteered for charity, and we believe it is different. Okay. So a type 1 error, if the researcher concludes that the proportion of Americans that participates in charity is not 62%, but it is actually 62%, that is a type 1 error. The type 2 error, if our sample evidence leads the researcher to believe that the number who participate is different than 62%, when it actually, wait, I just did this backwards. Say, leads the researcher to believe the current percentage is actually 62%, but they said it wasn't, then that's a type 2 error. I don't like the wording on this one. Let's do another one. Okay, let's look at the cell phone calls. Now we're looking for the greater than. This is that believe it has increased. Type 1 error occurs if our sample evidence leads to the researcher to conclude that the mean is greater than 3.25, but the average is actually 3.25 minutes. That's a type 1 error. So type 2 error, if the researcher fails to reject the hypothesis that the mean length of a phone call is 3.25 minutes, but it's longer than that, that's a type 2 error. So you fail to reject when you should have reject, type 2 error. Didn't reject when you should have, type 1 error. And it's two problems. And as long as you give it the college try and follow the directions about giving context, I'm going to give it to you. Most people lose the points because they don't reference whatever the story is. All right. Because this is not the big takeaway. It's something I need to test you on, but it's not the big takeaway from this unit. So just minuscule little deductions. All right. The probability of making a type 1 error is alpha. See, this is actually a good page. Type 1 error, rejecting H naught when H naught is true. Type 2 error, rejecting H naught, not rejecting H naught when H1 is true. Alpha is the probability of making a type 1 error. Beta is the probability of making a type 2 error. And these are just symbols. And since I'm not giving you guys this quizzes in a full term, I give you guys quizzes, but this moves way too fast for all these little quizzes every week. That's why I'm not doing that. But I don't believe there's any questions that are going to ask you this. But alpha is the probability of making a type 2 error. Beta is the probability of making a type 1 error. So you remember back in chapter 9, we were doing Z sub alpha divided by 2. That alpha is actually my type 1 error probability. That's what that alpha stands for. And with just a confidence interval, it's not really meaningful. But when we're dealing with hypothesis testing, it's pretty meaningful. And we don't really use beta all that much, so we're just going to kind of throw that one out. But the alpha, that is going to be our level of confidence, which we're going to call it something else in a minute. But our level of confidence is based on whatever that probability is, that alpha. So I'm always going to give you the alpha, so don't even worry about it. You do not have to come up with alpha on your own. All right. Yeah, probability of making a type 1 error is chosen by the researcher. We call it level of significance. As I just said, we were changing it. Instead of confidence level in this chapter, we call it level of significance. And that is the alpha, which is the probability of making a type 1 error. I am not going to ask you this question of what does alpha stand for. You're just going to know that that's your level of significance. All right. I know I'm moving through these slides fast, but we don't have to do math. So it's like Some of it requires a little extra time and some of it doesn't. So some of it we just can kind of just slide by, enjoy our Tuesday evening. In other words, the probability of making a type 1 error increases as the probability of the type 2 error decreases and vice versa. They are related to each other. I'm not going to ask you this on a test, so you can just nod your head and smile and we'll move on. Okay, this is important, so important. We never ever accept the null hypothesis. Never ever. You reject or you fail to reject, or you reject or you do not reject. We do, just like you don't ever declare a defendant innocent, you declare them not guilty just because you don't have enough evidence. And I don't have every single sample out there, or I don't have the whole population. So I could have just gotten a good sample that supported my null hypothesis. It's still possible that the null hypothesis isn't true. It's just that my sample that I have doesn't disprove the null hypothesis, if that makes sense. I just don't have enough evidence. That person that is on trial for stealing Amazon packages off people's porches, he he might be the one doing it. We just don't have enough evidence to show it. Therefore, he's not guilty. It doesn't mean that he's innocent. It just means that based on the evidence, he's not guilty. So based on the evidence, we will fail to reject the null hypothesis. So don't ever say we accept the null. We never ever accept the null. We fail to reject or we reject. Say we do not reject or fail to reject. I just like the words fail to reject better. And when you take your test, you are going to be writing out a conclusion. You please very, very specifically tell me whether you reject or fail to reject the null hypothesis. I want it very explicitly stated. I want it really super clear that you understand what's happening, that you are rejecting or you are failing to reject. Make it very, very clear. Pretend that I'm handing it off to some TA that doesn't know what we talked about in class and he isn't sure, and my key says fail to reject or reject. Okay. All right. What are we doing now? Oh, we're going to do conclusions. Now, I firmly believe that textbooks are written in a way that they get paid per word. Have you ever thought this when you see people, how many words people use in textbooks to get a point across? It's like they must be being paid per word. Everything is so wordy. Their conclusions to these hypothesis tests are so wordy. Yes, they do take a lot of words, but they don't take nearly as many words as the textbook gives us. So I will write out what works for me on each one, and I will explain what I'm looking for, like on a test. But the conclusions I write here, because we're not going to have the math yet, they're not going to be fully complete. Once we have the math on Thursday, it'll be fully complete, if that makes sense. Okay. So in this case, this is the cell phone one that they believe that the mean length of a call has increased since then. Our sample evidence indicates the null hypothesis should be rejected. Look at how many words they use. So here's what I would write. There is sufficient evidence. Now, if we were writing this after doing the math, we're going to explain what the evidence is. But we haven't done the math yet. That the mean length of a call of I'll say cell phone call is greater than 3.25 minutes. Therefore, we reject the null hypothesis. Bam. I mean, it's bigger than theirs, but it is fewer words. Theirs is, it, in my brain, theirs is a little confusing because they restate the alternative hypothesis and then they restate the null hypothesis. And it's just a lot, but saying there's sufficient evidence. Now, you could even simplify this a little more, but I'm going to have you state what the evidence is and then state that you reject the null hypothesis or fail to reject. Once you know what that evidence is, which is the math we're going to do, you'll say, here's my evidence. Because of this, I failed to reject the null hypothesis, or I reject the null hypothesis. All right, I think I have one more. Yeah. So now we're going to do this one saying it should not be rejected. So now we're going to fail to reject. Okay. So there is not sufficient evidence to conclude the mean length of a call is greater than, my handwriting's really bad, sorry, 3.25 minutes. Therefore, we fail to reject the null hypothesis. There we go. Okay. Questions on the conclusions? Okay. All righty. You know, it's weird as a math teacher that this is probably our third class this term where we've actually done no math. It's just kind of weird as a math teacher to actually like three classes teach no math. Okay, we are now in 10.2. You have enough material, enough information to complete the 10.1 assignment. It's basically going to be writing null, the hypothesis, the null and the alternative hypothesis, choosing which one it is, choosing whether it is a right-tailed, left-tailed, two-tailed. You might be choosing conclusions. I'm not sure. You will be choosing, determining if something's a type 1 or type 2 error. So it's all, there's no math, it's all words. So that's what's happening in that one. Now we're going to move on to 10.2. 10.2, we're not doing the complete thing because we're not going to actually do the math. But I mean, um, we're not going to be doing the math. We're going to stop before we get to the actual math part. I'm going to show you what it looks like to how to determine whether or not we reject the null hypothesis without actually doing all the math behind it. And I will show you the outcomes and we can make those decisions. Okay, so our researcher obtained a simple random sample of 1,000 people. They found 534 were in favor of banning cell phone use while driving. So about 53.4%. Does this suggest that more than 50% or favor this policy? So in this case, our null hypothesis in this case would be that 50% would favor banning cell phones while driving. But our sample shows it's 534 or 53.4%. Therefore, this is going to be a right-tailed test, right? Because 53.4% is greater than 50%, this would be a right-tailed test. It's okay. It's it's the evening. Okay. So what we want to know is what it's asking me. Is it possible that the true proportion of registered voters who favor this policy um, is less than 50%, even though this survey is showing it's greater than? Would it be unusual to obtain a sample proportion of five, 53.4% or higher? Would that be unusual? Would it be statistically significant? This is what we're asking. This is just what's in our brain. I'm not asking you to answer it. This is just where our brain's going. Okay. What statistically significant means is that the probability of getting a sample like we have, if the given proportion, the null hypothesis was true, if it was actually 50% and we got a sample that was 53.4%, would that be unusual? Would that be our probability of that happening be small enough to make it unusual? That's what we're looking at. If it is, if it is that probability is small enough to make it unusual, we call it statistically significant. So if I did all of the math and I found out that there was only a 2% chance of getting that sample if the null hypothesis was actually true, that would be statistically significant, and I would have to reject the null hypothesis because it would be unusual to get a sample like that, given that the actual percent is 50%. Does that make sense? Okay, good. So I look for the first things we're always doing these, and I'm going to pound this into your brain even more as we go further. So, the first thing we do, just like we did in 8 and 9, is the first thing we do is we do this. Is it normal? Remember this right here is normal. Is it normal? Um, our NP times 1 minus P is greater than 10. So we're good. That tells us it's normal. And that it says 1,000 is significantly smaller than population. It is less than 5% of the population. Therefore, it's independent. Remember, those are the two things we need to test, normal and independent. Good, we're good. Our mean, because this is our null hypothesis, our mean is going to be 0.5. Good, that's great. This is our standard deviation. We're using the same new standard deviation that we used before, but we are using our sample size and our null hypothesis because we cannot use anything else as long as our null hypothesis is our truth. And our null hypothesis is our truth until we prove it isn't. Okay, makes sense? Okay, so that's where we are right now. We have our mean and we have our standard deviation. So I'm going to set it up. This right here is my confidence interval. Remember, I told you we weren't doing math yet, so I created a confidence interval. So there we are. If my sample, I'm going to get a different color because I'm bored with red. If my sample information lands me out here or out here, that's statistically significant, and we reject the null hypothesis. The edge of my confidence interval is 0.516. It's 534, right? 0.534 is what my sample gave me. It is outside of my confidence interval, so it is statistically significant. Therefore, I would reject the null hypothesis. I would say it is not likely to get a sample like that if my null hypothesis was true. Therefore, my null hypothesis is probably not true, if that makes sense. So that's where this is what we're doing. This is what the math we're doing is going to reveal to us. If my sample lands outside that confidence interval, then we reject. We're not always going to use one standard deviation. We're going to use the significance level to determine the edges of my confidence interval. So this one just decided that that's where it was, this example. but depending on what your significance level is going to determine where the edges of, kind of like we did in chapter 9. Our edges are going to be determined by that. Yeah, we're going to use Z scores and T scores just like we did in chapter 9. Our confidence intervals are going to look slightly different because, and this is a good time to bring it up. So on a one-tailed test, let's say I have a right-tailed test, this right here is the whole alpha. Because we're just using the right tail, we'll use the whole alpha for that. But these are alpha divided by 2 because this is a two-tailed. If it's a two-tailed test, we have to divide that alpha by 2. But if it's a one-tailed test, either right or left, we don't divide the alpha by 2 because we only care about the top half here. And I'll get into it more as we're actually mathing it, but that was a really good question. Thank you. Okay. So these are our two ways of checking. These are two different ways that we're going to determine whether our hypothesis test, whether we fail to reject or reject. So in this case, we're not going to do one standard deviation. We're going to talk about different alphas. So one of the ways that we do this, we check if something is too many standard deviations away from our mean. So in this case here, my confidence interval was one standard deviation away from the mean. So if I have a value that's more standard deviations away than the edge of my confidence interval, then I would reject it. So if my z-score, let's say the edge of my z-score, so my z sub alpha divided by 2, let's say it's 1.96. These are not the actual numbers for this problem. I'm making them up. Then my sample, I'm not giving you the symbol yet. My sample gives me a z-score of 2.08. This 2.08 is beyond the 1.96. This is the classical approach. Therefore, I would reject the null hypothesis. Let's say, let me take a different sample in your brain. Let's say different sample, diff sample. This is a different problem. If I had a sample z-score of 1.85, that is not as extreme. It's before I hit the edge of my confidence interval. Therefore, I would fail to reject the null hypothesis. I wouldn't reject it because I'm inside. I'm less extreme than that z-score. This is what the classical approach does, if that makes sense. Okay. So this right here, the z-score that we did with 0.534 is 2.15. That's more than 2 standard deviations away from the mean. So we're saying it's very extreme. So we are rejecting the null. Now, the z-score we're using to compare it to depends on our significance level. We're not using those numbers yet. We'll use those Thursday, but we compare it to whatever the z-score of my significance level, we compare it to the sample. If the sample's more extreme, either positive or negative, we reject. If the sample is less extreme, positive or negative, we fail to reject. So I could have a one-tailed test. Let's say this is not with this problem. Let's say I have my mean right here and it lands out here. So let's say this right here was negative 1.96 and this was negative 2.34. That negative 2.34 is more extreme. So it's outside of that confidence interval. So we would reject. Does that make sense? Okay. All right. So we do have another approach. And another approach requires us to actually find probabilities. So this one right here, the probability of being more than 2 standard deviations away from the mean, or being 2 would be 0.228. So I know the empirical rule says it's 0.25, but remember it's an estimate. Empirical rule is an estimate. This is when we have both sides. So the empirical rule is an estimate. It is close to 2.5%, and we just call it good because it's numbers that we can remember. So that area in the tail is also a probability. The probability of something landing out there is 0.228%. So, or 2.88%, 2.28%. Man, I can't speak. So if that's less than whatever my significance level is, we're gonna reject. You'll see in a second. So I'm gonna move on. So I just already told you this one. We're gonna do the p-value approach. So the second criteria. So if we have something called a p-value. A p-value is just a probability. P-value is just a probability. So if my probability makes it highly unlikely or unusual, if the probability of getting that sample is unusual, then we reject the null hypothesis. So we just had that was 0.0226. So if my alpha, let's say that I have an alpha of 0.05, let's just say my alpha is 5%, and my p-value 0. I'm just going to keep this number 0.0226. This probability is less than my alpha. Therefore, I would reject the null hypothesis. Because the probability of getting that sample is less than the predefined alpha, we will reject the null hypothesis. Let's say that for a different sample, for a different problem, I got a p-value. I still have an alpha of 0.05. The p-value is 0.058. That number is larger than my alpha, so I would fail to reject. Because comparing it to the alpha, it is not unusual. So we have those two approaches. On the test, I'm not going to care which one you use. You can use whichever approach you want. As we start doing math with it on Thursday, you're going to have a favorite because I know I have a favorite. I'm going to try not to be biased here, but you're going to have a favorite. You're going to choose one that makes more sense to you, and you can just use that one on the test. I don't care which one you use. They're both accurate. They're both fine. And on Thursday also, I'm going to teach you fancy calculator functions. I know you like those. Fancy calculator functions, I will teach you those as well. And it will give you your p-value, so it's good. But you can determine, would I rather look at the probability or would I rather compare the z-scores? My open math is going to tell you which one to use. So you get to practice both of them on your homework. So you'll get to do a little bit of practice with both of them, and you're going to choose a favorite. You're going to figure out, this one I feel confident doing, so this is what I'm going to use on the test. So, because I don't care either way. I think one problem says to give me either the z-score or the p-value. You can give me either one and both answers are correct. Same thing when you write your conclusion, you can give me either one because it does not matter to me. So we move on. All right. So here, I landed out here. So that I'm looking for the probability that my sample, my p-hat, remember p-hats are estimates or samples. So my p-hat, what is the probability my p-hat is greater than 0.53 or 0.5? So I found the z-score, which we don't have to calculate first, and it got a probability right there. That is absolutely less than 5%. Therefore, I would reject the null hypothesis. The results are unusual. Therefore, we're going to reject the null hypothesis. I think that was the last one. Yeah, if the probability of getting a sample proportion is as extreme or more extreme than what we get with the null, then we reject. We're going to do all the math with it, and I think it's going to make even more sense on Thursday once we do all the math, because that's usually when it really starts clicking, right? All of these words are not super helpful, but it's really a great lead into it. So I'm out of slides. Anybody have any questions for like regarding what we just went over, or for on the record, on the recording? Okay, I'm going to stop the recording now. Everybody else, you're going to miss out. We're probably going to talk about really cool stuff. I don't know. We might not.